Yes, sir.
Good morning, everyone, and welcome to the lecture. Am I audible and visible to all of you? You can see me?
Yes, sir.
You can see the screen? Okay. Um, what we were discussing in the last class? Do you remember?
Resistivity and conductivity of conductor. We have completed, sir. Semiconductor.
What we have done?
We have done conduction in conductor. Resistivity and conductivity of semiconductor.
Did we do P-type, N-type semiconductors?
We have to start now PN junction, sir.
So we are already done with what is the P-type semiconductor and what is the N-type semiconductor. Am I right?
Yes, sir. Sir, how is your health, sir?
I'm a lot better than what I was yesterday. Not perfectly fit, but yeah, I'm okay. I'm okay.
Okay.
How about you guys? You are doing good?
Yes, sir.
Good. Stay healthy. Eat properly, sleep properly, and you will be all okay.
Okay,
Okay.
sir.
Speaking of that, we are talking about P-type and N-type. We saw that there are two types of semiconductors: intrinsic, which are pure; extrinsic, which are impure. They have got impurities doped onto them. We have got two types of impurity:
Yes, sir.
pentavalent
PN
impurity,
and junction.
trivalent impurity. If you have pentavalent impurity, you have one electron more. We have then we call that impurity or that type of semiconductor as N-type. Electrons are the majority charge carriers, holes are the minority charge carriers, and we reverse it. If we have a trivalent impurity, we have one electron less, therefore it is known as a P-type semiconductor. Isn't it correct?
Yes, sir.
Now we had to start PN junction today, and by the looks of it, when you hear the word PN junction, what comes to your mind? What would be a PN junction? Everything that we talk in physics is very obvious. What do you think a PN junction is? What do you think a PN junction is? Tell me, bacha. What would be a PN junction? The understanding comes from the word itself, PN junction. So I will have a P-type semiconductor in which holes are the majority charge carriers. I will have an N-type semiconductor. I will combine them, join them, fuse them. Whatever I have would be known as a PN junction. Yes or no? Yes or no?
Yes, sir.
That's simply PN junction. Now we will see what all things we need to see again. I must tell you very frankly, semiconductors, electronics is a huge branch. We're only going to do a very small part, very brief part, right? So a PN junction, you'll have P type, you have N type, and you combine them, you get a PN junction. There are two methods. This question has come in your AIMS as well as your AIPMT and your NEET. What are the two methods of making a PN junction? The first method, as you can see, is the alloy method. Why my thing is not the first method is alloy method. In this, what will happen is you have an N-type semiconductor, and on top of that, you put something, you melt it, and you get a PN junction. That is known as the alloy method. You melt something, you have N-type or you have a P-type, and you put other type on top of it and melt it. You call it the alloy method. Do you understand this?
Yes, sir. Repeat, sir.
Right? You have an N-type, you put small P-type on top of it and melt it. You have a PN junction. You have an N-type, you put a P-type on top of it, you have a PN junction. You understand this?
Yes, sir.
That is known as the alloy method of creating a PN junction. Then there is the second type, which is the diffusion method. And in diffusion method, what do you see? You diffuse it, you heat the P-type semiconductor, and you put it inside the vapors. So this N-type will get diffused. don't have to go into what the actual process is, because the actual process is not a part of your syllabus. You must only know that there are two methods. One is the alloy method. In alloy method, you put one and you put other on top and melt it. In the second method, you have one p type or n type, and then you have vapors of the other thing coming. We understand this? We don't have to go into much details of this. You just have to know that there are two methods of creating a PN junction. Shall I move ahead?
Yes, sir.
You don't have to know. You don't have to draw any diagram. You don't have to draw any diagram. You just have to remember that there are two methods of creating a PN junction. That is all you need to see. Again, now this diagram, you may draw this diagram that is coming up next, because there is a very important concept of a depletion layer in this, and you'll have to understand this depletion layer. There would be questions coming on this. So please understand what is this. So what do you see here? Do you see a PN type, a PN junction here? You see a P type and you see a N type. Do you see this? Yes or no?
Yes, sir.
So you have a P type on the left hand side, you have a N type on the right hand side, and you are creating a PN junction. Do we understand this?
Yes, sir.
In the P type, we have holes, which are the majority carriers. In the N type, we have electrons, which are the majority carrier. It has more number of electrons. It has less number of electrons. This has more number of electrons, or you can say this one has more number of holes. Now, when you combine this, so what will happen? Some electrons will travel from right to left, some holes will travel from left to right, and in between this space, what you see here is they will overlap each other. Do you see this?
Yes, sir.
Some electrons have come on this side and some holes have gone on this side. Do we understand this?
Yes, sir.
As you can see the description, the P region has majority holes and the N region has majority free electrons due to the concentration diffusion. You understand the meaning of diffusion? Things going from one side to the other side. Diffusion, it is getting diffused from P type. From P side, holes are moving to N side. From N side, electrons are moving to P side. Do we understand this?
Yes, sir.
Due to this, a layer of only positive in N side and negative in P side starts to form, which generate an electric field which opposes the diffusion process. During diffusion, magnitude of electric field increases. Basically, after some time, what will happen? In the beginning, negative charges are going from N type to P type. Positive charges are moving from P type to N type. This process will continue, but after some time, this process will stop, and then you will have a layer between that junction, between that P and N junction. You will have a layer in which you will have no free electron and there is no free hole, because they have neutralized each other. That layer is known as the depletion layer. So this blue thing that I have done is the depletion layer. Do we all understand this?
Yes, sir.
Any doubts on this? So depletion layer is a small section of the PN junction where this PN junction is getting joined. In this small region, there is no charge. Holes and electron, they neutralize each other. This layer or this small region is known as the depletion layer. Do we understand this?
Yes, sir.
Everything depends on this depletion layer. If I can, and we will see what will happen if I do something on this depletion layer, what will be the effect of this. You have to understand what is depletion layer. So please draw the diagram and just write this is the depletion layer. Okay,
Okay, sir.
just note this down. Small things you have to note down, because question will only come from these small things. Have we drawn this diagram? Bacha? Okay, I'll give you a minute.
We are doing so.
Have you noted this down, Bacha?
Yes, sir.
Everyone noted this down? Shall we move ahead?
Yes, sir.
Okay, sir. So now these are the important points that you must remember about this depletion layer. Question based on this will come directly. The width of this depletion layer, when we have shown it very big, but the range of this is 10 raised to the power minus 6 meters. No one is going to ask you this range probably. But what they can ask you, what will happen if the temperature increases? So remember this point, if the temperature is increased, depletion layer also increases. The reason is very simple. When the temperature increases, more holes will move from p type to n type and more electrons will move from n type to p type. Do we understand this? Because they have more energy and therefore the depletion layer will increase. Do we understand this, bacha?
Repeat, sir, please.
Okay. So as temperature increases, just remember this, as temperature increases, the depletion layer also increases. We understand this? Temperature
Yes, sir.
increases, width of the depletion layer increases. You just have to remember this. Next very important point is PN junction is unohmic, does not obey Ohm's law. I and V, the relation between V and I is not linear. V is not equal to IR. Do we understand this?
Yes, sir.
The next thing that you must understand is something known as potential barrier. If I have to move from one side, from P side to N side, or from N side to P side, how much energy or potential I must need? So potential barrier for germanium is 0.3, for silicon is 0.7. No one is going to ask you this. Just remember this. Electric field, no one is going to ask this. This electric field prevents the charges from crossing over to each other. Once this depletion layer is formed, charges cannot flow from one side to the other side because of this barrier. Do we understand this?
Yes, sir.
Once the depletion layer is formed, charges cannot move from one side to the other side. That is the entire thing that we need to understand here. Nothing else, nothing less, nothing more. Okay? We get this? Now what I
Yes,
need
sir.
to do is probably change the size of this. Otherwise, I will not be able to show you this. So I probably change the size. Just give me a minute. Just change the size of this thing. Have to decrease it further. So, uh, I hope that you can see it. Okay, rather than increasing the size, you have the sheet with you, right? The sheet that we are doing, the sheet is there with you, yes or no?
Yes, sir. We have sheets.
Okay. So you can see it from the sheet. So I will not, because it is getting too small for you to see. You will not be able to see it. So what I'm going to do is I'm going to show it to you in parts rather than show it the entire thing, because it is just becoming too small. I would not be able to write anything. Now there are two types of current that you must understand. The first type of current that you must understand is known as the diffusion current. Now remember, when we talk about current, we talk about the direction of current. What is taken as the direction of current? In which direction does the current flow? What do we understand it when I say the direction of current? The direction of current is actually, if we talk practically, electrons are flowing inside the circuit. So direction of current must be the direction of flow of electrons. But that is not how we take the direction of current. Do we remember this? Yes or no?
Yes, sir.
So we take the direction of current as the direction of flow of positive charge. Yes or no?
Yes,
Yes
sir.
or no?
Yes, sir.
Similarly here, when I talk about current, remember the direction of current is the direction of flow of positive charges. Now here we are talking about, it's a PN junction. We are talking about two currents. One current is the diffusion current. Holes are moving from P to N side. Do we understand this? Holes
Yes,
are
sir.
moving from P to N side. That current is known as the diffusion current, which happens on its own. That is known as the diffusion current. From P side to N side, whatever charges are flowing, the direction of current from P side to N side, that is known as the diffusion current. Do we understand this? Just remember this. The second type of current is drift current, which is from N side to P side. When there is no biasing, now you'll say, sir, what is biasing? We'll come to that. If there is no biasing, then both this current cancel out each other. So one current is going from here to here, the other current is coming from here to here. They cancel each other out, and therefore the total current is zero. Do we understand this?
Yes, sir.
Please note it down. I'll give you a minute. Two types of current, diffusion current. Don't get confused. A straightforward question will come. What is the direction of diffusion current?
P to N side.
Yes, sir. Please don't forget it, sir. Otherwise, it will be a big problem, sir. Okay, sir?
Okay, sir.
And now, please note it down. Acha. Diffusion current and drift current. Diffusion current is from P to N side. Drift current is from N to P side. We just need to understand this. And now we come to the most important part of this chapter, and we will be dealing with that part. Remember, beta, as I've told you, this topic is huge, humongous. I'm only trying to cover those parts which are important and which have come in your exam previously. Do you understand this? And which I think can come in your exams. I'm only concentrating on those, and I'm letting go the parts which may not be so important. In any case, you have the entire sheet with you. Entire thing is covered word by word. You can go through it. Have you written that diffusion current and drift current? Yes or no?
Yes, sir.
Yes, sir. No, sir. Then, sir, we come to the part, sir. Just now, what we saw, when the PN junction is isolated, nothing is connected to it. Diffusion current from P to N and drift current from N to P, they cancel each other out and there is no current. Yes or no?
Yes, sir.
Now what we are going to do is, and we had used the term biasing there. Biasing. Well, what is this biasing? And here comes the next hero, biasing. What is biasing? This is biasing. There are two types of biasing. One is known as the forward bias. One is forward, the other one will be reverse. Now, what is a forward bias? The diagram is right there in front of your eyes. There is a diagram. Do you see the diagram? Yes or no? Shall I make it bigger, or is it good enough for you to see the diagram? Do you see the diagram, bacha? Yes or no?
Yes, sir. Yes, sir.
Okay, I'll not make it bigger because my mouse is not working, so I have to do it with the mouse pad, and I'm not very comfortable with the mouse pad, so just not resizing the screen. Forward biasing, there is a battery that has been drawn. I have written positive and negative. Now I wrote it so that you can understand it on your own. What do you mean by forward biasing? That is very evident. What do you mean by forward biasing? And you should never forget that in your entire life, what is forward biasing. What is forward biasing? How I've connected the PN junction? That is what I'm asking you. How I've connected the PN junction? What is forward biasing? The material is also written. Can anyone tell me what is forward biasing?
P side is connected to positive, N side is connected to negative.
That is correct. When I connect my P side to positive and then I connect my N side to negative, in that case, what happens, bacha, is that P side is connected to positive and N side is connected to negative. The applied voltage is opposite to the junction barrier, as you can see. This is the applied voltage, and the junction barrier is like this. Due to this, the potential barrier or the depletion layer decreases. Junction width decreases, potential barrier decreases. So more carriers can flow through this junction. It means the current flows in principally due to majority charge carriers, and it is large. So now majority charge carrier holes can move from P side to N side because they have potential now. Electrons will move from N side to P side because they have potential now. This type of biasing, this type of connection to the battery is known as positive bias. When P positive is connected to positive and negative is connected to negative, depletion layer decreases, potential barrier decreases, more carriers can flow. That is known as forward biasing. Do we understand this?
Understood, sir.
1 minute, sir. Note it down, sir. You have to draw the diagram also, sir. In the diagram, the dotted lines that you see was the original potential barrier, original depletion layer, and it has decreased. Do we understand this, that the potential barrier has decreased?
Yes, sir.
Yes, sir. Please write it down, sir. I'll give you a minute, sir. Have you noted it down, bacha?
10 seconds.
Yes, no? What, sir? Noted, sir?
Done, sir.
Done, sir. Now, if one type of biasing is forward biasing, what will be the other type of biasing known as? It will
Reverse
be known
bias.
as reverse biasing. Yes or no?
Yes,
In
sir.
reverse biasing, what will happen? Negative N type is connected to positive terminal. We understand this.
Yes, sir. Opposite.
Opposite. And P type is connected to the negative terminal. So what will happen? The applied voltage is same as that of the junction barrier. Effective potential barriers is increased. Junction width is increased. So no majority carriers will be allowed to flow across the junction. Only minority carriers will be drifted. That means the current is due to minority carriers and is very small. Do we understand this? Just the reverse of the entire thing. Yes or no?
Yes, sir.
A minute, sir. Please note it down.
Done, sir.
Then, sir. Then, sir. This, sir. Something that you must remember about reverse bias. As you can see, the current is very small. Current is due to minority carriers, depletion layer increases, potential barrier increases. We understand this. There is one very important thing that you must understand, that is known as the Zener breakdown, and that is what we are going to see. In reverse bias, what is going to happen? The current is very small and nearly constant. This is known as the reverse saturation current because it always remains same. Whatever you do, the current will not change. Do we understand this?
Yes, sir.
But an important thing happens if the reverse bias is increased beyond a further limit. If you keep on increasing the reverse bias voltage, that means the N type is connected to positive and P type is connected to negative. I increase the battery, I increase the value of this voltage. If I keep on increasing this, there will be a condition when the depletion layer will break down. The voltage becomes so high in the reverse bias that the depletion layer will break down. This condition is known as the Zener breakdown. It was discovered by scientist C. Zener, and it is known as the Zener breakdown. This diode is known as Zener diode, and we have questions based on this Zener diode, and we will be seeing those questions. Do we understand this?
Yes, sir.
Then there is one more. So this is Zener breakdown. There is another variant of Zener breakdown which we will be discussing once you write this. So what you are going to write in reverse bias, the current is almost constant. It is known as the reverse saturation current. But if you keep on increasing the value of voltage, at some point the depletion layer will vanish. This is known as Zener breakdown. Please note this down up till here. Note it down, bacha.
Completed, sir.
Completed, sir. Then there's another type of breakdown which is known as avalanche breakdown. Avalanche breakdown. Now, what is the difference between avalanche and Zener? Just listen to it. There's another variant of Zener breakdown. It's a type of Zener breakdown. If there is low doping concentration, if the doping impurities are very low, you can just simply understand this. Just remember this, if the doping is low, then the breakdown is known as avalanche breakdown. Do we understand this? Just remember this. If the doping is low, then the breakdown becomes, or the breakdown is known as, which breakdown?
Sure.
This is
Avalanche
known as
breakdown.
avalanche breakdown. Yes or no? Just remember this. And then there is a table here, and we'll discuss this table. Nothing here that you have to understand. Everything here is what you will have to remember. Because there can be a question, they will give you a condition and they will ask you what type of breakdown it is. Is it Zener breakdown? It is avalanche breakdown? It is this breakdown, that breakdown? Then you will have to tell them which breakdown is this. Are we ready for this?
Yes, sir.
Here it comes and we will just discuss this. So what happens in Zener breakdown? Here covalent bonds of the depletion layer break. Do we understand this?
Yes, sir.
Here covalent bonds of the depletion layer are broken by the collision of minority charge carriers. No one is going to ask you this, but just remember collision of minority charge carriers. Whenever you see this term, collision of minority charge carriers, then it is avalanche breakdown. Got this?
Yes, sir.
Here the doping is high, here the doping is low. Do we understand this?
Yes, sir.
Here the voltage is lower compared to the avalanche breakdown where the voltage is high after breakdown. So after Zener breakdown, the low voltage is low. After avalanche breakdown, the voltage is very high. Do we understand this?
Yes, sir.
In Zener breakdown, the depletion layer almost breaks, so it
Thick
is
depletion
very
layer
thin. Here the depletion layer is thick. Do we understand this?
is thick. Yes, sir.
Everything is what we have discussed. Just note it down. A straightforward question will come, bacha. Please remember what we have learned. Just note it down. I'm giving you time. Make the best use of this time. Note it down, bacha.
1 minute, sir.
1 minute, sir. Okay, sir.
Done, sir.
Done, sir. Then, sir. As I told you, the most important aspect of this chapter is forward biasing and reverse biasing. For the question always comes from this. So we'll just see the important points for forward biasing and reverse biasing. You can see a question. Do you understand what is forward biasing, bacha?
Yes, sir.
P is connected to positive, N is connected to negative.
And
Yes or
power
no?
for negative. Yes, sir.
Okay, so I'll not go further into this. We will just see the points and you will note down super fast, because with these points, every question that comes that I have seen coming is covered very beautifully in the points that we are going to see. I'm just resizing it so that you can see it. Bada size matters. Okay, here it comes, and I'll just dictate the points one by one. In forward biasing, this is forward biasing, potential barrier reduces, yes or no? Are we there in the class?
Yes, sir.
So if it reduces here, it increases here. Width of the depletion layer decreases here. Width of the depletion layer increases. We all understand this. PN junction
Increases.
gives very small resistance because very large
Small
current flows.
resistance.
PN junction gives high resistance. Forward current will flow. Very small current will flow. Order of current is milliampere. It is very high. Order of the current is nanoampere. Mainly majority current will flow here. Minority current will flow. Do we understand this?
Yes, sir.
Please note them down, sir, so that I can move on to the characteristic curve, which is a very important aspect of this chapter. Characteristics curve. Many questions have come on this characteristic curve, so we will cover it nicely. I'm giving you a minute to note it down. Everything comes automatically. If you understand, if you even remember one point, all the other points are coming from that one point. A minute, 2 minutes.
Done, sir.
Okay, sir. Then, sir, this curve, sir, as you can see, this is forward biasing wala curve. So voltage is shown as positive. Here it is reverse biasing wala curve. So voltage is shown as negative. Do we understand this?
Yes, sir.
Forward biasing means positive voltage. Reverse biasing means negative voltage. Do we understand this?
Yes, sir.
And this is the curve. As we increase voltage, what you see is current increases, but it is not linear. And after a point which is known as the knee voltage, if I increase the voltage more than that, the current increases tremendously. Do we see this?
Yes, sir.
And remember, V is not directly V is not equal to IR. The graph is not a straight line. Do you see it?
Yes, sir.
This is the forward curve. As you can see, this is the reverse curve. At this point, when you make the reverse current, reverse voltage to this point, you will have a very large current, and this is known as the breakdown voltage. Do we see this breakdown voltage here?
Yes, sir.
So this is the Zener breakdown or breakdown voltage. If you increase the reverse biasing current, reverse biasing voltage by a large amount, at one point it will break. That is known as Zener breakdown or avalanche breakdown. Do you see those two graphs? Yes or no?
Yes, sir.
You have to draw these two graphs, sir. And I'll give you a minute for that. A minute to win it. Have you noted down, bacha?
Done, sir.
Done, sir. Then, sir, this thing, sir, you'll have to understand what is forward resistance. Forward resistance means resistance in forward bias. Reverse resistance means resistance in reverse bias. Do we understand this?
Yes, sir.
Forward resistance RF is forward voltage divided by forward current. As you can see, forward resistance is very low. Reverse resistance is reverse voltage divided by reverse current, and it is very high. Do we understand this?
Yes,
Then
sir.
we have seen this knee voltage. You don't have to remember the values. The breakdown voltage is also given. You don't have to remember the values. No one is going to ask you these values. Forward current equation, again, this is not in your course. If you want, you can note it down. Else, you can let it go. The only thing you must understand here is the reverse resistance and the forward resistance. Apart from that, everything I don't think is a part of your course. Okay?
Okay, sir.
You just note down forward resistance and reverse resistance. That is what you need. Please let me know once you have noted down.
Sir.
Done, sir.
Completed, sir.
Okay, sir. Then, sir, we, sir, have a look at this one, sir. Now, this is how. Now, we call it a diode, PN junction diode. Di means two, ode means this thing. Diode, triode. Diode means two, ode. Triode means three, ode. So, diode, it has a P and an N junction, one P and one N. So, it has got two poles. So, it is known as two diode or the diode. Now, how do we represent this? It is represented in this symbol, the arrow and one danda after the triangle. That danda becomes the N side and that triangle becomes the P side. Do we understand this?
Yes, sir.
This is forward biasing, complete circuit. This is reverse biasing, complete circuit. You may not understand it. You just understand that it is forward bias. And how do you understand? You look at the positive side and you look at the P side. If positive is connected to P, that is forward bias. Do we understand this?
Yes, sir.
Here, if you see positive is connected to this line, that means this is reverse bias. Yes or no?
Yes, sir.
You don't have to draw the diagram, but this is the combined diagram. What we have done, we have drawn the diagram of forward bias and reverse bias. In the previous thing, we had drawn the diagram separately. Forward bias was different, reverse bias was different. Here we have combined the two, forward and reverse bias. Do we understand this?
Yes, sir. Understood.
So you just draw this one, you just draw this one, and you draw this one, and you just understand this one and this one. Have you understood these two arrow wala? How they are forward and reverse biased? That is more than enough if you have understood this. I hope you have understood this.
Yes, sir.
Yes, sir. Note it down, sir. Have we done this?
Done, sir.
Done, sir. Then, sir, this, sir, very important thing, sir. So we understand that a diode can only function in the forward direction. Yes or no? When it is forward bias, then only it works. Yes or no?
Yes, sir.
If it is reverse bias, the current is literally zero. Yes or no?
Yes, sir.
And therefore, we can use this diode as a switch. When the switch is forward bias, the switch is open. It can conduct current. It can allow current to flow. It's a switch. When the diode is reverse bias, it is off because current cannot flow. So it is behaving just like a switch. Do we understand this?
Yes, sir.
So PN junction diode is basically a switch. In forward bias, the switch is on. In reverse bias, the switch is off. Will you remember this? Will you remember this?
Yes, sir.
Yes, sir. Then, sir, please, sir, note it down, sir, with the diagram, sir. And write, sir, that this is forward bias, sir. So this is on, sir. This is reverse bias, sir. So this is off, sir. Okay, sir. We agree
Okay,
on
sir.
this part, no, sir? Oh, yes, sir. I'll give you a minute, sir. I'll stay quiet, sir, till that time, sir.
Completed, sir. Done, sir.
Okay, sir. Done, sir.
Done, sir.
Then, sir, uses of this junction diode. Okay, we have seen one use already. What is that one use that we have seen just now? It can be used as a junction diode. PN diode can be used as a switch. Forward bias, it is on switch. Reverse bias, it is off switch. We understand this?
Yes, sir.
Then the next use is rectifier. Now, what is a rectifier? What is a rectifier? You know, there are two types of current or voltage: AC, alternating voltage, alternating current, and DC, direct voltage or direct current. Yes or no? Yes or
Yes,
no?
sir.
Now, if you see here on the top hand side, you have an alternating current. Now, what's the difference between alternating and DC or direct current? In alternating current, you will have a reverse in the direction of current. So for some time, the current will flow in this direction, and after some time, the current will flow in this direction. Do we understand this?
Yes, sir.
But in DC, current always flows in one direction. So this top wala diagram that you see is AC, and this bottom wala diagram that you see is DC. Do we understand this?
Yes, sir.
Why it is AC? In AC, the cycle will reverse. For one half, you will have current in this direction. For other half, you will have current in this direction. But in DC, current always flows in one direction. Do we understand this?
Yes, sir.
What is a rectifier? A rectifier is a device that converts AC into DC. Do we understand this?
Yes, sir.
Where is the rectifier used? Do you know any use? Do you know any use of a rectifier? Who is using who is using a rectifier? Where do you see a rectifier being used?
Systems, computer,
Where?
system, computers.
Laptop, yes, my laptop, this gentleman, it works on a battery. The battery is giving you DC voltage. When I am charging it with AC. Here is AC, inside it DC. Someone must be converting it. Who is converting it?
Rectifier.
A rectifier is there. That gold dabba, that dabba is there. I can't show it to you. That gold dabba is the thing that is converting it from AC to DC. Do you understand this?
Yes, sir.
Yes, sir. No, sir. Do you understand this?
Yes,
AC
sir.
getting converted into DC, that is a rectifier. Now, how it is done? There are two types of rectifier. One is known as a half wave rectifier. In half wave rectifier, what are we doing? This is the input. Do you see the input? Do you see the input?
Yes, sir.
And then you see this is the positive cycle. So positive is connected to p type, and therefore it will allow current to flow. In the negative cycle, negative will be connected to positive. It will not allow the current to flow. So for one cycle, positive cycle, you will have current flowing. In the negative cycle, there is no current flowing. Do we understand this?
Understood, sir.
Well done. When the positive cycle is going, the diode is forward biased. It allows current to flow. In the reverse cycle, it does not allow current to flow. So this device behaves as a half-wave rectifier. Half-wave rectifier, it means that one half of the wave is gone. The negative half of the wave, see this half of the wave, here, here, here. In the output, all these halves are absent. Do you see that?
Yes, sir.
That is known as a half-wave rectifier. Do we understand how this half-wave rectifier works?
Understood, sir.
Understood that? Now, it may take time for you to draw it. If you want, you can draw it. I'll give you a minute if you can draw it in that time. Else, we will move on. The diagram is already there in your what?
Sheet.
In your sheet, so you can see the diagram from your sheet. And remember that this is a half-wave rectifier, because when the question comes, it will be either based on a half-wave rectifier or it will be based on a full-wave rectifier. And here it how a full-wave rectifier looks like. Can I show you the full-wave rectifier? Can I? In half-wave rectifier, you only needed one diode. One diode was doing the job. One diode was doing the job. Can we move on to the full-wave rectifier, dear friends?
Yes, sir.
Yes, sir. This is how a full-wave rectifier looks like, bacha. We have got two diodes, diode D1 and diode D2. Do we understand this? Do you see two diodes here, D1, D2? Do we see two diodes, D1 and D2?
Yes, sir.
And sir, then you see, sir, what, sir? In the positive cycle, diode D1 is forward bias, yes or no? Yes or
sir.
no?
Yes, sir.
So D1 diode will conduct and you will have this yellow wala portion of the wave coming. Do we understand this?
Understood, sir.
Okay, sir. But sir, in the negative cycle, I will use pink color. In the negative cycle, this is negative. This is positive. So this diode D2 will conduct now. Yes or no?
Sir.
We understand
Yes,
this,
sir.
sir? And
Yes, sir.
therefore, this negative cycle wala part here will come over here, because the current in the final circuit always flows in the same direction. As you can see, the direction does not change. This is the final register, and you can see in first case the current was flowing like this. In the second case also current is flowing like this. So current ka direction has not changed. In first case it was through diode D1. In the negative half it is through diode D2. So I have converted AC, the full wave, into DC. Do we understand this?
Yes, sir.
If you can note it down, bacha, note it down. Else, the sheet is there for you. You can see it in the sheet. This entire chapter is about understanding the different types of configuration, and you will have to remember this configuration. The more you can remember this configuration, the better it is going to be for you. Shall I move ahead now, bacha?
Yes, sir.
Then another type of rectifiers, not another type of rectifier, I mean, we are doing the same thing in a different way, is known as the bridge rectifier. It is also doing the same thing. If you can see, And I showed to you during positive cycle, positive half, this diode is forward biased, yes or no?
Yes, sir.
So current will flow like this, like this, like this, like this, like this. It reaches here. Then you can see it will go. Where it will go? Do you see the current moving?
D4
Then the current,
goes for D4.
yes, goes for D4. And from here, it will come over here. Do we see this?
Yes, sir.
Yes or no? Now
Yes,
let us
sir.
look at the negative cycle. In negative cycle, I will just draw it by the red ink. This will become negative, yes or no?
Yes,
So the
sir.
current will now flow like this. Ding, 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 ding. It will go
Yes,
through
sir.
this. Yes or no?
Yes, sir.
Then how will it go? Then it will go straight. I think this it will go.
D3 to RL,
Yes,
and then D2 and D4.
yes. So we understand this, how the current is flowing.
Yes, sir.
So it goes like this, like this, like this, and it comes back. Okay. So a bridge rectifier or whatever we have seen, they are just converting AC into DC. Do we understand this?
Understood, sir.
Understood, everyone? Shall we move ahead?
Yes, sir.
Here we have to understand one more thing is this form factor. So you just write this formula for the form factor.
Two questions.
Yes, beta?
Let's do some questions.
Form factor. This is the formula for form factor. All these are questions, beta. All these are questions. What we are doing is questions only. Right? All these are questions only. And we'll do all the questions together because we can't jump back from here to there. The number of questions are too much. So what I'll suggest is you do the exercise that I've given you on your own. Okay? Everything
Okay,
there
sir, we will do.
is basically theoretical beta. So what we are discussing, the same questions will come and we'll do them. Don't worry. But let us finish the theory part first, right? Let us finish the complete theory part, then only you can jump on to questions. But what we are discussing, the same thing will be coming in the questions. You got this?
Yes, sir.
If they are numericals, we will discuss them. Otherwise, everything else is theory. And I hope you have started solving the questions as well. Yes or no?
Yes, sir.
Yes. So you start solving the questions and I will cover as many questions as possible in one class. We will do. Let us finish with this. And in one or two class, we'll do all questions. Okay. So
Okay, sir.
for full wave rectifier, the form factor is this. For half wave rectifier, the form factor is this.
Pi by 2.
Yes, so you just have to remember these two values. Again, as I told you, beta, most of the questions that we see here, everything is based on how much you know and how much you can remember. There is nothing that you can understand. So you will have to remember here, beta. It's all electronics. So you'll have to remember things. The more you can remember, the better it will be for you. Do we understand this?
Yes, sir.
Okay. So again, we'll go through some terms. You have to remember these terms. Ripple and ripple factor. In the output of a rectifier, both AC and DC might be present. when we have AC and DC both coming, we call it ripple, and the ratio of AC to DC is known as ripple factor. The ratio of how much AC is coming divided by the ratio of how much DC is coming is known as the ripple factor. Now, for a good rectifier, the ripple factor must be very low. That means it has to remove the entire AC component. Do we understand this?
Repeat, sir.
For a good rectifier, ripple factor must be very low. Ripple factor is AC component divided by DC. For a good rectifier, AC must be 0 or very low, and hence the ripple factor must be very low. We understand this?
Yes, sir.
Then, so you remember this, for a good rectifier, ripple factor must be very low. For a good rectifier, ripple factor must be very low. Total output current is I square AC plus I square DC ka root. RMS value, we don't know our RMS value because you would not have done AC. We'll do it, then you will understand this. Right now, just remember the formula. Ripple factor is current of AC divided by current of DC. Have we seen this? Yes or no?
Yes, sir.
So this is I RMS square by I square DC minus 1. You just remember the formula, nothing else. There's nothing that you have to understand here. Okay?
Okay.
There's nothing that you have to understand here. Just remember this. This I RMS by I DC is the form factor. For a half wave rectifier, I RMS is this, I DC is this. For a full rectifier, I RMS is this, I DC is this. Ripple factor is this, ripple factor is this. You just have to remember them. Not the values. You have to remember the I RMS and I DC values. There is nothing that I can help you with this. You will have to remember this. Do we understand this? Because the question might come and they might ask you straightforward values. I cannot help you if you don't remember it. There are also other things given, but we will not be doing it. I'll just give you the formula for efficiency. I don't think other things can come. Have you noted this down, bacha? Have you noted down, bacha?
Done, sir.
Okay, sir. Then you just remember the formula for rectifier efficiency. Efficiency is always output divided by input. Here output is DC, input is AC. So power of DC divided by power of AC. So this is the formula that comes. DC power is I square DC into R. RL matlab load current, load resistance. Input is I square RMS into RF. The forward bias wala resistance plus the RL load wala resistance. Just remember these formulae. Don't ask me how they have come. I will not be able to explain this in the short time that we have. We understand this?
Yes, sir.
Just remember the important points that I am telling you, bacha. These same questions are going to come and you will see them. I will show it to you. They see same question has come, and then you will feel, wow, same questions are coming. Are we done, bacha?
Done, sir.
Okay, sir. Then, sir, very important point. Question will come on this. What is ripple frequency? The output frequency of rectifier is known as the ripple frequency. Whatever frequency the rectifier gives in the output, that is known as the ripple frequency. For a half wave rectifier, see, this is the input. Positive cycle, negative cycle. This is the output. You have one positive cycle, then you have no cycle, then you have one more positive cycle. As you can see, the frequency remains same. Do we understand this?
Yes, sir.
But for a full wave rectifier, you have positive cycle and negative cycle. Here you have two positive cycles. Therefore, the frequency has become twice. Do we
Changes.
understand this?
Yes, sir.
Please note it down. Very important point. Question will come on this. Have you noted it down, bacha?
Give me 30 seconds up.
You're copying it? Okay.
Yes, sir.
I'll give you a minute. Don't worry.
Completed, sir. Written.
So we have seen what happens to the frequency. In case of an half wave rectifier, frequency remains same. In case of a full wave rectifier, frequency becomes twice. Yes or
Double.
no?
Yes, sir.
Then again, one more thing, pulse. Pulse. You will be dealing with pulses. Pulse. For a half wave rectifier, this is one pulse. No, this is two pulses. But for a full wave, output, you will have only one pulse. So two pulse becomes one pulse in half wave rectifier. Do we understand this?
Yes, sir.
Pulse becomes half, but frequency remains same. Do we understand this?
Yes, yes, sir.
Pulse becomes half, but frequency remains same. We understand this?
Yes, sir. Frequency
Don't forget
remains
this.
same.
I'll give you a minute to note this down.
Done, sir.
Done, sir. Now, sir, we look at what happens to a full wave rectifier. Input, you have two pulses. Output, you have two pulses. Frequency become twice, but number of pulses remaining same. We understand this?
Yes, sir. Frequency double.
We understand this?
Yes, sir.
Please note it down, sir.
Done, sir.
Done, sir. So, sir, what, sir, now, sir? I'll give you a glimpse of what we are going to do in the next class. Uh, all these things may not come in the examination. Also, what I'll ask you is to do them at home as homework. All these filter circuits, capacitor filter circuit. So, what do you have here? You have an output from a rectifier, which we have seen full wave rectifier, and then you put it through this circuit. Filter circuit is nothing that I have to make you understand. The output becomes like this. Do we understand this, bacha? Just have to remember this. You got this? This is known as the capacitor filter. We understand this?
No, sir.
You just have to remember this, sir. Okay, sir?
Okay, sir.
There is nothing that I can do. Again, this is an LC filter. So in an LC filter, the diagram is like this and the output is like this. There is nothing that I have to make you understand. You just have to remember this. Yes or no?
Yes, sir.
Might not get a question on this ever, but you will have to just remember the diagram. This is a, oops, this is a pi filter and a T filter. Do you see this? Pi filter, the best filter, and T filter. So remember, pi filter is the best filter. Yes or no? No one is going to ask you these complicated things, but you have to understand what is the input and what is the output. You don't have to understand this maybe, but you have to understand what is the input and what is the output. Can you do that for me? Yes or no?
Yes, sir.
So if you can do that for me in the next class, I will not be discussing this. And in the next class, I will be beginning with the Zener diode, which is a very important aspect. Most of the questions in numerical will come from the Zener diode. If you get time, also read the Zener diode so that we can move faster in the next class. Can you do that for me? I've already told you what is Zener diode. Yes or no?
Yes, sir.
The only thing is the symbol of the Zener diode is somewhat different. For a normal diode, the symbol is like this. But for a Zener diode, it becomes like this. Do we understand this?
Yes, sir.
And you know what is a Zener diode. If we can go through this, it will help a lot for me to carry on with your exercise because we'll have to complete this course. I have to complete this semiconductors in 2 classes maximum. Okay, so we'll try to do that. So if you can do this Zener diode on your own, it will help me out. Will you do it?
Yes, sir. We will do.
And also start with the exercise. Start doing that exercise. I'll do them maybe tomorrow if I finish with this, or maybe day after tomorrow. Okay.
Okay, sir.
Okay, then I'll see you in the next class. Take care and have a nice day. Bye bye.